Astrid, are you ready?
I am.
Okay, let's start. Okay, good morning, good afternoon, and good evening. Welcome you again to this World River and Delta System Source to Sink webinar series. And this is Paul Liu from NC State University. This webinar series is co-sponsored by ISF, North Carolina State University, Louisiana State University, State K Lab of Estuarian and Coastal Research, and Utrecht University. So today, we are very honored to invite Professor Astrid Blom from Delft University of Technology, come here talk about river response to peak flows and climate change. So as always, before I introduce Astrid, I would like to mention our all previous talk, including this talk, have already been archived. This talk will be, of course, on our YouTube channel, Source to Sink YouTube channel, also on the Bilibili station. So feel free to use them as your research and education teaching purpose. At the same time, we have also maintained a Source to Sink Twitter account. As you can see, all announcement talk will be announced over there. You are welcome to follow us. So we have basically 1,500 followers. That's a pretty good number. And so next week, next Wednesday, at the same time, Alice Lefebvre from University of Bremen will come here talk about morphology of estuarine dunes. So in particularly with the estuarine Germany. So as I mentioned, Astrid is an associate professor now at Delft University of Technology. She graduate from over there, master degree, and also 20 university PhD, Netherlands, and then postdoc over there, then studying as assistant professor, associate professor at Delft, and now is the section head, river, ports, waterways, and dredging engineering program. So her research mainly focused on the anthropogenic modification and the natural change effect the river equilibrium state regarding channel slope and bed surface grain size, as well as the river response with time to that kind of change. He kind of loved to develop a conceptual and analytical models to particularly try to understand how the physics governing the modern and historical river problems. That's as a C, he combined the models and lab field observation data, numerical model, extend the physical understanding of engineering applications. So, okay, I think Astrid, now I give the floor to you. Please share your screen for the presentation mode.
Thank you so much, Paul. I'm very pleased to be able to give this talk. Let me choose full screen mode. Is this all right?
Yeah, very good.
All right. Now the title of my talk is River Response to Peak Flows and Climate Change. And the subtitle is Equilibrium, Quasi-equilibrium, and Transient Channel Geometry. There will be contributions from Enrica Fiparelli, Lieselot Arkestein, Matt Sapiga, and Claudia Ilia-Arbos. So thanks to those. I have 6 topics that I will discuss with you. First is the phases of river response. Then I will talk about equilibrium geometry, about quasi-equilibrium response of rivers. Then I'll move to the impact of variable flow rate, so the hydrograph. And then I'll discuss the transient phase, everything between the initial response and the equilibrium response. And then we'll shortly discuss river response to climate change. Right, first some general remarks about river response and how a river responds to natural change and measures. It can do so in three ways. First is by adjustment of channel slope, then by adjustment of channel width, and of course it can change its bed surface texture. And it can change its channel slope by channel tilting. So it's like this movement, this motion, and it can also change its channel slope through a change in sinuosity. This would then change the length and so channel slope. It can change its channel width by a difference between the inner band accretion rate and outer band erosion rate. And of course, it can fine or coarsen its bed surface. Now, in this talk, I will mostly be focused on engineered channels for which the planform is fixed. And not only planform is fixed, but also width is fixed. And this means that such engineered rivers or channels can only adjust through slope adjustment through channel tilting, and it can adjust its bed surface texture. Now let us first have a look at the Waal branch of the Rhine system in Europe. And the Waal branch is found, it's the lower branch in that small square. And here you see a plot of the floodplain area in blue-green. You can see the amount of floodplain area that was taken from the Waal branch and the IJssel branch since the year 1850. So you can see it's quite a significant amount of space. And not only floodplain area was taken away, but also the main channel was narrowed by the construction of groins. Now we're interested in how a river channel adjusts to such change. And here you can see how the Waal bed level, the main channel bed level, has adjusted through time. So on the horizontal axis, it's streamwise position. Right-hand side is upstream, left is downstream. And you can see how it has adjusted its bed level from 1950 to 2010. And the erosion rate is between 1.5 and 3.5 centimeters a year. In the erosion rate. Now, the remarkable thing here is that it's not just an erosion that you see, but it's a slope adjustment. And you see that channel slope has decreased with time, and the erosion is actually a result of the channel slope adjustment. Now, we would like to understand why such slope adjustment occurs. And how that could be attributed to the channelization and narrowing of the past. But before we go into that matter, I would like to discuss with you some general specifications of channel response. So we can distinguish between three phases of response. First, there is the initial response, and this is defined as the stage where only the flow has had time to respond. And the bed is about to start adjusting towards the new equilibrium state. Then there is the long-term response, and also called the equilibrium response. And it was originally called the concept of grade by Gilbert and Mackin. And it's the state where the channel has adjusted its slope such that it can transport the supplied sediment downstream. And it's actually not only the channel slope, but also bed surface texture. So it's the state where the channel is able to transport the sediment supplied from upstream in downstream direction. So there's no reason for further change if an equilibrium state is achieved. And the controls of this equilibrium state are the flow duration curve. The flow duration curve is the PDF of the flow rate, the probability density function of the flow rate, the average flux or supply of gravel and sand, averaged over years or decades even, and the downstream water level, so also called the base level. So those are the controls of the equilibrium state. Now, if these controls vary around stable mean values, then this equilibrium state is a dynamic one. So it has a static component and dynamic fluctuations around that static or quasi-static state. And for that reason, equilibrium also needs to be considered over a period of years or decades because of these dynamic fluctuations around that quasi-static state. And now there's a special case of equilibrium or subset that we call quasi-equilibrium, a quasi-equilibrium response. And a quasi-equilibrium response occurs if the rate of change of the controls is very slow. So for instance, maybe a climate change that could lead to a very slow change of the flow duration curve. And if the channel is able to keep pace with that change of the controls, then the channel is able to remain in a quasi-equilibrium state at each moment in time. And this is what we call a quasi-equilibrium response. So there's a slow change, but the geometry is defined by equilibrium conditions at each moment in time. And then there is the transient response, and this is the phase in between the initial response and the equilibrium or quasi-equilibrium response. Now it's important to realize that this transient response is not leading or governing the equilibrium state. So it's actually the controls that we just mentioned that are determining the equilibrium state. What is also important to recognize is that if there's a change of an upstream control, that this will typically lead to downstream migrating adjustment waves. And when there's a change in the downstream control, like base level change, sea level rise, for instance, that will typically lead to upstream migrating adjustment waves. All right, let us dive a bit deeper into equilibrium geometry. Now we discussed the case of channel narrowing and channelization as occurred in the Rhine system in Europe. Here you have you see a small schematic of such a narrowed reach. And we would like to be able to determine what the specifications of the new equilibrium state would be under a situation of such narrowing. And we can actually do so by looking at the conservation equation. So we're not actually looking at the details of these equations, but we typically consider the conservation equation of sediment mass, conservation equation of water mass, and streamwise momentum. Then, as we are interested in an equilibrium state, we know that all time derivatives in these equations must be equal to 0. So we can erase the time derivatives from these equations. And then what remains, we can combine with a sediment transport relation. And we can actually take any relation, but here we take the Engels and Hansen sediment transport relation because it's a nice and cute one, and it's a very simple one without a criterion for incipient motion. So it makes the analysis a bit more simple. But we can do this analysis for any load relation. Now, if we combine those relations, we find expressions for the equilibrium flow velocity, equilibrium flow depth, and equilibrium slope. If we look at the latter one, the equation for the equilibrium slope, you can actually see that once a channel gets narrowed, so channel width B is reduced, that will also lead to a reduction of the equilibrium slope. And it makes also sense from a physical perspective because for a narrow channel, a smaller equilibrium slope would suffice to transport the sediment downstream, as Gilbert or Mackin would state it. So this makes sense. Now, this we can do for any sediment transport relation, and we've done it for a number of load relations. And of course, here you see an expression for the equilibrium slope, but it's the downstream water surface level, the base level, that sets the absolute elevation of the river profile, right? So we understand why the Dutch Waal branch is undergoing a slope decrease as a response to the channel narrowing and channelization of the past. All right, now let's see if we can extend these relations to mixed size, to conditions with mixed size sediment. Before we have a look at those relations, we need to agree on a number of phrases, or I will introduce a number of phrases. So particle abrasion is the mechanism where gravel size gets reduced while gravel is migrating downstream or transported downstream. So particles hitting each other or hitting bed sediment reduces their size very slowly. Grain size selective transport is another important term. It expresses the fact that the mobility of sediment depends on particle mass or size. Fines are typically more mobile than coarse sediment, and therefore the load, the transported sediment, is typically finer than the bed surface sediment. Now, often there's some confusion about the term hiding, but hiding is the mechanism where fines become less mobile because they hide, and they become less mobile compared to a unisize case, and coarse particles become more exposed, they stick out more from the bed, and they become more mobile than in a unisize case with only that type of sediment. So hiding actually reduces grain size selectivity and the mobility difference between gravel and sand. Now we know that natural systems are typically concave upward, and this means that the slope reduces in downstream direction. And there's a lot of empirical relationships that describe that downstream decrease of slope, and the downstream decrease of slope often goes together with the downstream decrease in mean grain size. And the first empirical expression was listed by Sternberg. Now, Morris and Williams have collected a wide set of data relating this downstream finding to the concavity of the river profile. And here you see the result, and you see a nice band around the data, and you see a nice correlation between the downstream decrease in slope and the downstream decrease in mean grain size. Now let's see how our simple analysis compares to those data. So we can again look at the conservation equations, and now we don't only deal with conservation of bed sediment mass, but we deal with conservation of gravel in a top layer, conservation of sand in a top layer, and the two other conservation equations are the ones for flow, and those remain similar as in the previous case, and we add terms that describe abrasion of gravel. Again, we reduce those equations by looking at the steady state, the equilibrium state, which means that all temporal derivatives are set equal to 0. And again, we combine the resulting equations with a sediment transport relation, now one that is suitable for mixed size sediment. Here we take a fractional version of the Englund-Hansen equation. It's a bit of a homemade equation, but we can do so for any load relation, and this serves the purpose for today, and it keeps it nice and clean and simple. And then again, we find expressions for the equilibrium flow velocity, equilibrium flow depth, equilibrium slope, and now also an expression for the equilibrium grain size distribution of the bed surface. We can do so for any load relation, as I mentioned. We can also do it for more than 2 grain size fractions. We can do it without abrasion. And of course, these relations should reduce to the case of unisize sediment if we deal with 1 grain size only. And if we then compare the outcome of this analysis to the data sets, to the data set of Morris and Williams, you can see that the results nicely plot within the band of data found by Morris and Williams. All right, now, so far we had a look at engineered channels only, where those can adjust through channel tilting and finding or coarsening of the bed surface only. But let us assume that there are that natural channels, or that channels either adjust through slope adjustment or with adjustment. So let's assume that the valley slope sets the channel slope, and that natural rivers adjust through with adjustment only, respond through with adjustment only. Here you see those two cases. So let's consider it two end members of the real situation. So the first case was the previous case where channels respond through slope adjustment only, and there you see that an increase of the representative water discharge would lead to a decrease of the equilibrium channel slope, and that makes sense because for an increased flow rate, a smaller channel slope suffices to transport the sediment downstream, as Mackin would say. Now, if we deal with a channel that only adjusts its channel width and keeps its slope constant, you see that a larger representative water discharge would lead to an increase in channel width. This is something that would make sense to us, but we can also see that the channel width is pretty sensitive to the increase in flow rate. All right, now the real situation is probably in between these end member states, and one would need an additional relation, a closure relation, to close the problem. All right, now let us have a look at the relevance of this equilibrium analysis for the quasi-equilibrium response. So quasi-equilibrium was the case where we defined that the rate of change of the controls is so slow that the channel geometry can keep pace with the change of the controls. And we're going through a thought experiment. So here we consider a gravel sand ridge in its equilibrium state. So everything is peaceful. The channel is able to transport the supplied sediment downstream. There's no reason for further change. Now, what will happen eventually on the long term if the upstream sediment supply rate increases? Now, in order to be able to transport that increased sediment supply downstream, we expect that the new graded state, the new equilibrium state, is governed by a larger channel slope. So the new equilibrium state will be governed by a larger channel slope, and this will be achieved by an aggradational wave migrating downstream. Now, let's continue this thought experiment a bit more, and let's look at a sandbed ridge where suddenly gravel is transported into the ridge from the upstream end by the flow. And the total supply rate is kept constant. So the sediment flux arriving from upstream is becoming coarser. Now, what would we expect to happen in the long term? Again, we would expect the equilibrium slope to increase because the channel would need a larger slope to be able to transport that sediment downstream. Now, the coarse sediment arriving from the upstream end will build a larger slope until the channel is able to transport that sediment downstream. So a coarse wedge will form for which the slope starts to increase, and it increases until the coarse sediment can be transported downstream. So the coarse load requires a large upstream slope, and this wedge will migrate downstream until the channel reaches this new graded profile. Now, we believe that this process that we observe here in this case is a representative of what we call a gravel sand transition. And the first one that recognized or observed a gravel sand transition in the field is Yatsu. He recognized the gravel sand transition amongst other rivers, the Kinugawa River in Japan. And here you see a sudden, in the lower right-hand plot, you see a sudden decrease in grain size from gravel, sudden drop to sand. And this goes together with a sudden drop in slope, right? So the fact that the two go together, the decrease in slope with the decrease in grain size, makes sense, but we have a chicken and egg problem here. Now we've built based on that hypothesis, we've built a gravel sand transition migration model based on the conservation of sediment mass in that gravel wedge. The details of the conservation equations is not so important, but what I want to stress is the fact that we were able, with combining this conservation equation of sediment in the gravel wedge with equilibrium relations for the two reaches, so the upstream reach, the gravel reach, and the downstream reach and the sand reach, we were able to reproduce the gravel sand transition migration as appeared from a more complex numerical model, as you can see here. All right, so the equilibrium geometry is not only relevant for the equilibrium state itself, but it's also relevant for quasi-equilibrium conditions. Now, let's make a step toward the variable flow rate. Because of course we realize that the flow rate varies strongly as a function of time and space, but here we consider the temporal fluctuation. Now, as soon as we deal with a varying flow rate, we must recognize that there are typically three typical segments that we can distinguish in a river. Now, here we deal with a very schematized a river section. So there's no confluences, no bifurcations, nothing whatsoever. But we deal with an upstream boundary and a sea at the downstream end with a constant base level. The fact that there's a constant base level at the downstream end means that with the varying flow rate, the downstream flow depth deviates from the equilibrium flow depth, simply because of the fact that it's constant. And this will yield a backwater curve in the backwater segment. So during peak flow conditions, there will be an M2 backwater curve. Flow will accelerate in downstream conditions, in downstream direction, which will lead to erosion of the channel bed. And during base flow conditions, there will be an M1 backwater curve with deceleration in downstream direction, and sediment will deposit. In under equilibrium conditions, this deposition and erosion during peak flow, those will balance each other over time. So it will be a dynamic equilibrium state in that backwater segment. Now at the very upstream end, so let's assume that there's maybe a confluence or there's just an upstream boundary in a numerical model. It doesn't really matter. It can have a numerical origin or a natural origin, but typically there's a mismatch between the time series of the sediment supply, maybe because of that confluence at the upstream end, or it can also have a numerical reason, the fact that we simply provide the model with a time series of the sediment transport rate that doesn't match the time series of the sediment transport capacity. And this mismatch, this temporal mismatch, creates the formation of an upstream boundary segment where there will be downstream migrating waves migrating through the system. If there is space in between the upstream boundary segment and the backwater segment left, this is what we typically call the quasi-normal flow segment. So this is the area where there's not much change of bed level during the variable flow rate, but the flow depth breathes with the variable flow rate. So water level is going up and down, but there's not much change in bed level. And we can assume the flow to be quasi-normal. And I have a small animation here. Let's see if this works. So here you see an animation of the three segments. Oh, no, it doesn't work. Let's see. Let me try again. Yes, now it works, luckily. So it's really nice to see what happens in this schematized reach. So here you see now it's under base flow conditions, and it switches between base flow and peak flow. And you see that during peak flow, the flow accelerates. So it's taking sediment from the bed, it's eroding, during base flow conditions. There's an M1 backwater curve, sediment is depositing. I must say that bed level change is exaggerated by a factor 20 so that you can actually see it. Sorry, I will show it one more time. Let's also have a look at the upstream boundary segment. So here there's this temporal mismatch between the time series of the sediment supply rate and the sediment transport capacity. So you see downstream migrating waves, and they take a certain distance for them to disperse and get diffused. And what remains is the quasi-normal flow segment, where there's not much change of bed level during the variable flow rate. All right, and of course, this is a very schematic river profile, but let's have a look at real data. This is I will show some data for the Niger River, the Niger Benue system, and here you see measured water levels at 3 flow stages, here you have Lokoja as the confluence of the Niger and Benue system, and you clearly see. So the orange lines are water level lines for 3 flow rates, and you can clearly see a backwater dominated system at the downstream end. Now there's a few other interesting remarks that I can make about these typical segments, because they don't only form, or backwater segment doesn't only form right upstream from the downstream base level. It actually forms upstream also from confluences, from bifurcations, from significant changes in width, because all those transitions, so bifurcation, confluence, transition in width, they all create conditions where at such a point there is a deviation from the equilibrium flow depth. And this will lead to a backwater segment in upstream direction. And right downstream from such a transition, from a bifurcation, from a confluence, right downstream, you typically find an upstream boundary segment. So the importance of these 3 segments it can be quite significant. Now, how can we deal with the variable flow rate in this equilibrium analysis? Now, typically the flow rate, of course, can be described by a flow duration curve. This is a PDF of the flow rate QW. But let's simplify for the sake of illustration. Let's simplify it to a bimodal flow rate. So here we have a base flow rate and a peak flow rate. The base flow rate has a probability of occurrence alpha, and peak flow rate, by definition, then has a probability of 1 minus alpha. And if we have this, if we deal with this bimodal flow rate, then we can write the average or mean gravel load as a function of these two flow rates. So the mean gravel load is the gravel load under base flow conditions times the probability of base flow conditions plus the gravel load under peak flow conditions times the probability of peak flow conditions. And the same, of course, holds for the sand load. Now, if we use these 2 simple expressions and we combine those with mass conservation equations under equilibrium conditions, just as we did for our previous analyses, those were for 1 flow rate. Now we deal with a number of flow rates. We combine it again with a grain size selective transport relation. And now, for the sake of simplicity, we combine it with the normal flow equation. So this means that the resulting equations are only valid in the quasi-normal flow zone, so upstream from the backwater segment. And we look at conditions where we would know the annual gravel and sand flux arriving from upstream, and we know the flow duration curve. If we combine this information, we again arrive at the definition of the equilibrium slope for those quasi-normal flow segments, and we also arrive at the definition of the equilibrium grain size distribution for the bed surface. So this is quite convenient. So we now arrive at an equation for the equilibrium slope under a variable flow rate, but we dealt with a situation with only two flow modes, so base flow and peak flow. But this equation can easily be generalized to the full PDF of flow rates. So the details of these equations is not important for now. But what is important here is that in the definition for the equilibrium slope, that there appears to be an equation for the dominant channel discharge. So this is what we call a channel forming discharge. And it also has a very clear physical meaning. So it's that value of a constant discharge that provides the same equilibrium slope as the full hydrograph does. So it's that value of a constant discharge that provides the same equilibrium slope as the full hydrograph does. So that's a very interesting parameter. All right, so here we see the importance of the variable flow rate and its impact on the equilibrium geometry of a channel. Now let us again have a quick look at the two end members that we looked at before. And now we don't look at the impact of the flow rate, but we look at the impact of the variability in the flow rate. So on the horizontal axis, you see the parameter, the standard deviation of the flow rate divided by the mean of the flow rate. And you can see that if we look at the two end members, so the first channel adjusts only through a change of slope, and the second end member only responds through adjusting its width. You can see that channel width is pretty sensitive to variability of the flow rate. And we can also see that the sensitivity to the sediment transport relation is not so large. So that gives some trust in our outcomes. All right, now this analysis of the variable flow rate was limited to the quasi-normal flow segment. So this is where backwater effects don't have an impact, right? Now, Lieselot Arkenstein was able to come up with an elegant expression of the equilibrium state under backwater conditions. And she did so by separating two temporal scales. So she recognized there's a quasi-static behavior in river geometry, and there's a dynamic component that responds to short-term fluctuations of the flow rate. And by separating the two, she recognized it's the flow duration curve that determines the quasi-static component. And it's the sequence of flow events that determines the dynamic, the short-term fluctuation around the long-term component of the equilibrium state. And she also recognized that channel slope cannot keep pace, cannot adjust or respond to short-term variations of the flow rate, right? So under these short-term fluctuations of the flow rate, we can assume that channel slope cannot respond that quickly. And if you make that assumption, you can arrive at a very rapid and cute space marching solution, just as it's similar to how we solved the backwater equation for flow only, but here this is a space marching solution of the full equilibrium state in a backwater reach. And here you see an animation of what the method does. So you move from downstream to upstream, and you solve for the equilibrium state, the equilibrium channel within a backwater reach, and also the change of the equilibrium slope within the backwater segment. All right. Now, let's have a look at the relevance of the equilibrium state for the transient phase. Let me check how we are time-wise. A few more minutes, I think. Am I all right, Paul?
It's okay, yeah.
Okay. The relevance of the equilibrium state for the transient phase. So this is the phase in between the initial phase, the initial response, and the equilibrium response, or the quasi-equilibrium response. Now, Matt Sapiga, he was a postdoc working with me. He looked at nourishment possibilities in order to mitigate the channel incision that you see in the upper right-hand plot. And nourishment is the addition, artificial addition of sediment to the system. And you can use several strategies to add sediment to the system. So you can spread it horizontally or along stream. You can also put it in one location. Of course, you can choose the grain size distribution if you would have that sediment available. And he looked at various schemes and checked what works best in order for us to mitigate channel bed incision if we would want that. And what he found is that, so this is clearly a transient problem, right? It's not just the initial response. Initial response is only the response of the flow and nourishments. The propagation of added sediment typically is a transient problem. Now we found that mitigation of channel bed incision is only successful when the associated change to the sediment flux, so associated with the sediment nourishments, yields an increased equilibrium channel slope. So here we see that the equilibrium analysis becomes relevant to the transient problem. So once sediment nourishments add sediment to the system and change the sediment flux in the system such that the channel equilibrium channel slope increases, under those conditions, sediment nourishments become useful and mitigate channel bed incision. Now, there's a few notes to add. So if one were to add sediment finer than the surface sediment, this would, of course, find the sediment flux in the system, transported by the channel. But this finding of the sediment flux typically makes coarse sediment more mobile. It becomes more exposed. And adding fine sediment to the system typically decreases the equilibrium slope rather than that it increases. And this means that adding fine sediment to the system enhances erosion. And this can only be overcome, this effect of enhancing erosion, if one were to add a large volume of sediment, because only then that increased mobility of coarse sediment would be compensated, and then the equilibrium channel slope would increase, and one would become able to mitigate erosion by adding fine sediment. So adding fine sediment can be useful, but one would have to do it in large volumes in order for the equilibrium channel slope to increase. Now, adding sediment coarser than the surface sediment coarsens flux clearly, and it increases the equilibrium slope. So it would help, you would expect it would help to mitigate channel bed erosion, but there is a but. It requires an even spatial distribution of nourishments, as adding coarse sediment to the system leads to enhanced downstream erosion in the transient phase. And this I will explain in the next slide. So if you add coarse sediment to the system, you coarsen the surface, which reduces mobility, sediment mobility locally, and it would lead to a reduction of the sediment supply to the downstream reach. And this means that reduced sediment supply to the downstream reach leads to erosion right downstream from the added coarse sediment. And of course, we recognize that this only happens for a temporary period, but this temporary period can be quite long because such a coarse wedge is able to migrate very slowly. So this is something that should be considered. So adding sediment to a system to compensate for channel bed incision is not a trivial problem. So adding fine sediment can be problematic because you increase mobility of coarse sediment and you may enhance erosion, and adding coarse sediment may enhance erosion, as you can see in this plot, also for several decades or maybe even longer. All right. Now a short note before I go to climate change. So as I mentioned, Lieselot Arkestein was able to distinguish between two components in channel geometry And this appeared to be very useful also for the transient phase. So one should distinguish between those two components of channel geometry and the flow rate. And you realize that channel slope and also surface texture, the bed surface grain size distribution, cannot keep pace with short-term variations of the flow rate. You're able to come up with a very rapid numerical solution of the river transient response that also provides solutions, or a numerical solution to, for instance, the propagation of nourishments. I won't go into the details of the method, but I can recommend having a look at this paper. Then a few words about river response to climate change, and this is something that Claudia Arbos in my group is working on. She's looking at the Niederrhein Waal branches of the Rhine system, and she's working on scenarios for the temporal change of the controls, so the hydrograph, base level, grain size specific sediment fluxes, scenarios for the internal boundary conditions, for instance, the Ponneren bifurcation, and also scenarios for intervention schemes in the future. She has adopted a cycled 20-year hydrograph in order to be able to study the effects of climate-related change on the system. And she has calibrated, as the system is currently not in equilibrium. Calibration is also not an easy thing, but she's calibrated the model against current degradation rates and also flow partitioning at the bifurcation and temporal change of it. And scenarios for the hydrograph are based on climate scenarios that were developed by other people. Here you see an illustration of the cycled 20-year hydrograph, and it has a particular flow duration curve that is similar to the measured 100-year time series. So this is the reason why she picked this particular 20-year series, as it is similar to the PDF of the full 100-year hydrograph. And then we've looked at KNMI scenarios for expected change of the climate and runoff and the hydrograph. So the grade analysis of Deltares has provided us with the change flow duration curves for 2050 and 2085. And we have used those changes and imposed those changes to our hydrograph and looked at the results. Now, here I will only share some preliminary results because she's still in the middle of this analysis. But what we see is that the increased peak flows, or the increased occurrence of peak flows, yield erosional waves, both from upstream and from downstream. Sea level rise yields an upstream migrating aggradational wave, as we would expect, and it has migrated upstream in the order of 80 kilometers over a period of 40 years. The downstream migrating coarsening wave that is already going on continues to advance, order 10 kilometers over the next 40 years. But what is most important is that the Rhine River's response to past interventions, so the channelization and narrowing over the past several hundreds of years, still strongly dominates the channel response to climate change. All right, my conclusions. So the river in equilibrium or quasi-equilibrium has adjusted its slope, surface texture, and channel width such that over a period of years, it can transport supplied sediment downstream. The relevant controls are the annual or decadal gravel and sand fluxes, flow duration curve, and base level. It's the flow duration curve that determines the quasi-static component of the equilibrium state, and the dynamics around that equilibrium state are determined by the sequence of the flow rate of the events. And then the separation among these two scales allows for a rapid space marching solution of the equilibrium geometry. And it also allows for a rapid, another technique, a rapid numerical technique to modeling transient river problems such as sediment nourishments. And maybe the overall conclusion is that is the fact that the relevance of equilibrium geometry is broader than equilibrium conditions alone, as it also applies to quasi-equilibrium and transient conditions. Thank you very much.
Astrid, thank you so much. This is a fantastic talk, particularly help us understand from the engineering point of view how the river responds to those human and natural intervention. And so this is great. Actually, you know, last month on May 11th, a colleague Thomas Hoffman, you know, gave a talk about the Rhine River, particularly the human impact. And he also mentioned about the dumping sand sediment to the river system. That's a very interesting, because many rivers now facing sand shortage, and like Asian, South Asian river, they facing a big sand mining. People move the sand from the river, and here in Europe, maybe not that bad. But you know, your analysis, this is, I think, is very useful. Maybe can also apply for some river, you know, people dredging, sand mining, you know, to understand equilibrium. That's very, very interesting and useful. Okay, now let's open to the audience. Now, if you have any question, you can go ahead to unmute yourself and go ahead to ask Astrid.
Hi, can you hear me? Yes. Yeah, I'm Bing Yuan from.
Go ahead, Bing Yuan.
Hi. Yeah. Thank you, Dr. Blom. A very interesting talk. About the first, about the part about the equilibrium. From my understanding, I think it's you use a constant width, river width, right? So the whole channel is constant, the width. Am I right, or it can also change?
It's temporary constant, but not spatially.
Yeah.
In the simplified examples that I showed, I didn't see any impact of a spatial change in width.
Okay.
But it is allowed to change spatially.
Okay. Because in general, you can see, for example, for some estuaries, you can see the funnel shape, right? The effect might also be interesting to have a look. And also the effect of tide. Do you think it's easy to incorporate the effect of tide into your model?
Yeah, I know that Zhengbing Wang of Delft University has looked into that problem.
Okay.
Personally, I wouldn't call it an easy problem.
No, not at all.
But no, he has worked on that.
Okay.
I believe for the uni-size sediment case and constant flow rate case only, but including tides. So that's a very interesting addition.
Yeah. Okay,
I've stayed away from that zone.
Okay, thank you.
Sorry for that.
No, thank you.
Good question.
Okay, next. Anybody? John?
Hi, Astrid. Fantastic talk. John Shaw here at the University of Arkansas. I'm with you on all of the theory that you've constructed here. My particular case, which is why I bring it up, is I'm dealing with river channels which the bed no longer has really any slope to it. I'm talking about extreme backwater near the mouth where the bed is actually getting shallower, and we've got extreme loss of discharge from distributaries, and sort of in that zone where your bed slope is say 0, how does that affect your model? You're still moving a lot of water, but the bed slope would suggest that the sediment transport is no longer as important. Or how would you sort of qualitatively think about that final most downstream deltaic region?
Well, that's a good question. Let's say a channel slope which is close to 0, and the backwater effect would then still create a gradient in the flow depth, right? So that would
and then the water surface slope for sure.
Yeah, by the water surface slope. Now I'm not quite sure. I think I would need some time thinking about this problem. I don't dare say that, for instance, that approach by Lieselot Arkestein, if that would suffice for your case, I would have to study a bit. Maybe we can chat later.
Yeah.
Okay. Tremendously thought-provoking, and well, let's hope to continue this soon.
Yeah. Actually,
Thanks.
a couple weeks ago, the Louisiana State Professor Xu, he presented a talk about that the river profile in the Mississippi River. Actually, the very low part of the Mississippi river mouth is the riverbed much higher than the New Orleans to Baton Rouge section. It's kind of like a small concave shape. Yeah, I think John knew that very well. So that's another interesting, scenario, maybe,
I would suspect that you would be able to arrive at maybe the same model, but I would need some time to think and maybe chat together.
Interesting. Anybody? Any other question? So Astrid, you mentioned when we dumped the coarse material to the river. So I agree with you. I mean, just that will be cost that kind of a little bit downsides the erosion. This is just like the coastal protection or river bank protection. If you put some kind of concrete or hard material, and at the foot, below that is cost strong stress is actually erode the bed instead of protect.
Yeah. And this is also what our German colleagues downstream from the Ivesheim Dam in the Rhine River found. So when the Ivesheim was constructed and finished, they quite soon started adding coarse sediment right downstream from the dam in order to compensate for the downstream erosion. And then they figured that they found out that adding the coarse sediment enhanced the problem rather than mitigated it. So they changed their strategy and started adding finer sediment that was sufficiently mobile and did not reduce the sediment flux to the downstream reach.
That's a very good point. The more study need to know, even the combination of the clay silt, a little bit sand, how to which material add to then can easy to reach equilibrium instead of creating more stress there.
Yeah,
that's very good. Anybody have any comments? Any? That's very interesting. Very nice, Astrid. I hope you can apply your model observation or even the data curve, the flow curve, to some large river, like John mentioned, or some small river in a situation like the sand mining, or even a little bit of mountains river like Taiwan or other place that will be expand our understanding of that river response to the human and climate change.
Well, extending it to mountain streams will also be a nice challenge, I think. Also not too easy.
Okay, so is this one from where is it from? From
this is the source of the Jamuna.
Oh, that's wow.
Yeah.
This is okay, cool. They're very nice. So Astrid, thank you so much. And again, I mean, this talk is also archiving on our YouTube channel. If you like to rewatch, you can go back to the YouTube channel to watch it. Okay, thank you very much. See you guys next week.